Listen very closely. The sound you're about to hear is your mind exploding. We're going to talk about modeling feature behaviors, and this is something that is easily confused, particularly if you've got an accent like I do. It can be difficult for some students to appreciate the differences in what I'm saying. We're going to talk about topology, not topography, topology. And topology is, important. It has to do with how well things function in GIS compared to how they function in reality. And this all kind of is wrapped up in this notion of how we model feature behaviors. So when we try to construct real data models that mimic the real world, if two streets cross, lines meet at an intersection. If it's an overpass, the lines still meet. If it's an underpass, the lines still meet. In reality, sometimes the lines that go over top of one another do not meet. So how do you deal with that? Well, there's some simple rules. As far as the GIS goes, if it's an intersection, you want a node there because it's an intersection. And if it's an underpass or an overpass, you don't want a node. But we also have other things that we have to model, like things like coincident boundaries. In other words, if we have one boundary between two features, but that boundary is a part of each feature, in the example here we have the boundary between West Virginia and Virginia. It's a single line, but it's the southeastern border of West Virginia, and it's the northwestern part of the northwestern border of Virginia. So while it's part of two different things, it's got to be the same thing, because you can't have a different line for each polygon because it's one line that separates them. And so we call this concept topology. Topology describes the spatial relationships between features. And what we're talking about here is things like adjacency, connectivity, overlap, and intersection. Adjacency means how features that are beside one another interact. Connectivity has to do with things like lines that cross and whether they actually cross, are they connected or not. Overlaps really shouldn't exist in topology, and that's where we have issues to fix. Intersections, much like we see in the lines, those are more issues of connectivity, whereas the overlaps are more issues of adjacency. And this all comes back to this notion of logical consistency, which describes how well features mimic real-world situations. And so usually this is confined to testing for topological errors, where we look for things like gaps and overlaps, undershoots and overshoots and dangles, improper intersections and pseudonodes and loops and lines and various things, so that we can find stuff that has a strong potential to not reflect reality. For example, if we look at the image in the left for the overlaps and the gaps, clearly if this was County A and County B, between County A and County B there's a single boundary. But yet we have some portion of the space that according to these lines belongs to both counties, and we also have some space that is in neither county. That's not acceptable because that does not logically mimic what happens in reality. And so gaps and overlaps are violations of logical consistency, and when we test for topology, these are things that should be identified for immediate correction. So how do we do this? How do we check for it? How does this all work? Well, we set up rules. Rules establish how these things should be related. And so we apply the rules between feature classes, and then we identify areas that don't meet the rules. And the rules can be simple things like no gaps or overlaps between counties. Here we have Pine Ridge and Bennett County, and these boundaries should match. And we also have South Dakota, and the Pine Ridge boundaries should match. There should only be one line there between South Dakota and Nebraska, and it should also be the line of the Pine Ridge Indian Reservation. But these lines don't line up. and they should. They should be coincident, but they're not. When we look at this vector data like this, there's two submodel types, if you will, that exist in vector data. One's called a spaghetti model, one's called a topological model. Spaghetti model is the simplest. You create a feature, and then you create another feature, and then you create another feature, and the features are just shapes. No one cares, no one tests, no one worries. If they overlap, if they have dangles, if intersections and nodes and those sorts of things are there. We manage errors in this environment by being careful and by editing things. In other words, we don't get most of them. In the other model, the topological model, features may be stored as simple objects that can also be complex ones, where they interact together, where we have established rules for how these things behave relative to one another. We have network rules for flows and directions and roads and all these sorts of things. And so we have a ton of rules, and we also have a lot of specialized tools that help us define the topology and fix the errors. So that when we have coincident boundaries, we don't have to worry about trying to draw them in. We create them using tools, and then we can test for them using rules. And at the end of the day, it makes for a GIS that's more reflective of reality.